All right, guys, so we're going to do the second lecture today on lithography, etching, and some deposition techniques. It's going to be a shorter lecture. We want to let you guys ask questions. And yeah, if you guys want to sign in now, please do. Let's get started. So here are learning outcomes, a bit more about photolithography detail, some etch technique differences from wet and dry, and as well as an overview of PVD. So piggybacking off what you guys learned on Tuesday, photolithography is the use of light to expose a photosensitive polymer for then further processing steps. By what we mean by further processing steps, you can see this graphic on the right. You can see how after the entire lithography process, there is an etch technique used here. You can see it by that concave substrate right there. So looking at the components of photolithography, we have the photoresist. This is the actual photosensitive polymer. You have your photomask, which is the quartz. It's a quartz glass with a chrome pattern, which is used to reflect the light, then creating the pattern. You as well have your aligner, which is the tool holding your mask and substrate simultaneously to ensure that our patterns from previously photolithography steps are matching to sequent ones. So for some quantification of the technology, you have resolution. This is the minimum feature size that can be transferred onto your wafer, and as well as registration, which is just measuring that alignment from one layer to another. Here, just so you guys get kind of a sense of the scope we're working with, we aim the smallest nodes now are about 3 to 5 nanometers, and this is repeated for 300 millimeters. This is about a difference in scale of about 10 to the 8. So that kind of just shows you just the difficulty we're working with, and that's why these tools can go for well over $200 million. So getting into a bit of the detail in the actual polymer now. So there's about 3 components in the polymer. You have your resin, or it's Novolac from the brand Novolac. This creates the actual polymer matrix. You have your solvent, silane. This is usually an aromatic compound, which lowers your viscosity and allows for better wetting and spreading of your resist equally across your substrate surface. And lastly, you have the actual photoactive compound, DQN. This undergoes a Wolff rearrangement. I can actually detail that right now. So if you guys look at the molecules on the top right, you guys see that nitrogen. That's pretty stable on its own. So with the energy we receive from the light, this pretty much gets bounced from the compound, leaving a carbon radical right here. This gets rearranged to a 5-sided ring now when the carbon moves up towards the double bonded oxygen. That double bonded oxygen with the carbon reacts with water in the atmosphere, leading to a carboxylic acid. That itself is an acid. When you put it in a base, it gets very soluble. The base we use is your actual developer, which you will use after exposing your wafer. So here I have a couple questions now that you know some of the chemistry and physics behind the actual polymer. I want to ask you guys, before we do exposure, we do a little bake. This removes the water from the substrate surface. I'm wondering, why do you guys think that is necessary now that you know a bit more about the actual polymer? And my big hint is think about the polarity about water, especially. Any takers? Any takers?
It doesn't look like it.
Okay. So the photoresist is actually a non-polar compound. So you remove the polar water molecules from the surface to get some level of adhesion between the two. Next, looking at another question for you guys. Why do you guys think the solvent is necessary in the photoresist?
Is it so that way we can create a even layer of the photoresist along the entire surface?
Perfect. Literally perfect. Yeah. So another thing about this solvent is following your spinning of the photoresist, you also bake off some of the solvent to get better contact alignment or just better light transfer to the actual photoactive region or photoactive compound in the entire polymer. So keep that in mind. All right. now getting to the actual exposure of the photoresist. So we use the Abbey criterion to help define what feature size gives you, helps define what feature size you can resolve. So basically your resolution. So this is dependent on both the incident wavelength. I think now for industry standard in the UV range, it's about 193 nanometers. In the lab, you'll use a mercury light source, which is also UV. And the lens numerical aperture also depends on your setup. There's about 3 different flavors of photolithography. You can do it directly in contact. You could do it just with a gap, and you can do it with a gap and some lenses. This all offers different numerical apertures. There's also different techniques of processing underwater and such that also gives you very different numerical apertures. So the quality of transfer is also dependent on the gap, as I mentioned before. Looking at just a basic example of no lenses, the larger your gap, the greater your light diffraction. You can see here on the bottom right, I show you 2 criterion that we use to define that light diffraction. The Fresnel, or the most left image, where you see this very kind of sharp bump, that is for a contact exposure. You can see the further you get, you can see when that light pattern does start to kind of devolve a little bit, and you do see a bit more diffraction in those vertical kind of interference patterns. Okay, here I also show a formula for the aerial image. That aerial image is the actual intensity from your light bulb, and that dose is what your photoresist and or pattern is necessary to actually transfer that pattern. So here I have another question. If our mercury lamp can output an aerial image of about 50 milliwatts per centimeter squared, and our photoresist requires a dose of 100 millijoules per centimeter squared, how much time do we have to expose our sample to?
Would it just be half a second?
It would actually be 2 seconds, pretty sure.
Oh, sorry, I read that backwards.
Yeah,
Yeah,
it
2
is
seconds.
too.
Sorry, I read that our lamp was providing 100 millijoules.
Yeah,
or
okay, I see
milliwatts.
it. Yeah.
Yeah,
So this is actually something you also calculate in the lab. I'm pretty sure Gila makes you do this, but he will give you the variables himself, like I just did.
no, I'm just an idiot, and I accidentally read the power output as 100 and are required as 50.
All good. Now getting into some of the patterns that we see and the differences between positive and negative resist. As you guys learned, well, as I've always been told, positive resist, what exposes goes, and for negative, what you're exposing is staying. So as I said before, light diffraction can come from that proximity change, but light diffraction also does come from that chrome on our photoresist mask. We do see a higher intensity of light in the center than we do see in the edges, as light seems to diffract from that chrome. Due to this, we don't get perfect straight vertical patterns in our resist. We actually get more of these like trapezoidal shapes. So the negative photoresist itself leads to an undercut. You can see it there, that kind of upside down trapezoid, while the positive gives us an overcut, which is that kind of concave shape. So these do serve specific reasons, and we do use them for exactly very specific reasons. So positive, we use an etching profile. Since we get the smaller or more, I guess, resolved feature at our substrate surface, we end up using that for etching. For negative photoresist, you can see that in the positive, when we do metallization layers, we have a complete coverage of metal. So it's hard to get into our photoresist and kind of develop that out. So instead we use a negative photoresist, as you still do have space to kind of wash away that photoresist itself. And you also see that since we're going to completely metallize our positive photoresist, when we wash away our photoresist, you do get some cusp and some tearing of the metal, which that doesn't happen for the negative photoresist. Just to add on to this process itself is not really used in industry. You guys do use it in the lab, and we'll do so in research. The industry itself will go for an etch step where they just actually metallize the whole substrate, put photoresist on top, expose that, then etch through that layer and through the metal. So just so you guys know. All right, now on to the wet versus dry etching. Give me 1 second. So wet etching uses strong acids and bases for atom removal. It's a purely chemical process. The pro here is high selectivity when it comes to the material you're etching. So if you're going to be etching a silicon dioxide with silicon underneath it, this is probably what you would use, as you can select high etching through the SiO2, but not through the Si. A con here is particle contamination. You are using a bath and your substrate is going to sit in there, and as well as low N isotropy, meaning that it's going to etch in each direction. You can see here with that cusp in the silicon, well, sorry, the silicon dioxide, that it's not just a vertical or purely one directional process. So here I show you guys an example of BOE wet etch, which will go through the SiO2. It has a selectivity of about 100 to 1. This is why we use it in the lab. Next, for dry etching, we'll go over the use of plasma and ion bombardment for atom removal. So the pro of using dry etching is you get high anisotropy. So for trenches or something with a high aspect ratio, this is what you would probably use. You also get low contamination as your substrate's not in any solution, as well as you're using most of your process in the gas phase. And a con is variable selectivity. There's a lot of chemistry that out there that can change your selectivity of your plasma, be it adding oxygen, changing the pressures, and changing the temperatures. Here, I tried to show you guys just how complicated these chemistries can get. For silicon, you can see of about maybe 15 samples here of different plasmas you can use to kind of etch material off that silicon. Silicon dioxide, same, about 5 examples, and so on. So here we get a bit more into the dry etching. So dry etching, it's a bit hard to kind of quantify what's going on. Plasma is a kind of tricky kind of science to get behind. There's about six atoms, radicals, and ions in it at any time. So to get a very comprehensive look at what's happening at the surface is kind of difficult, but we'll try our best. So plasma is initiated by arcing the feed gas. Most of the time, this is a reactive gas. The only time this is not is for an ion milling process. That plasma, for the most time, the gas in your chamber is going to be about 90% of your feed gas, about 10% of your neutral radicals, and a very low concentration of ionized species actually in that plasma. So for silicon plasma etching, we use fluorine ions. So we're going to input some chemistry with fluorine in it. CF4 is what a lot of literature uses to kind of describe it because it's kind of understood. In our lab, we're going to use SF6. But the big point is just getting fluorine to the surface. So once we ionize our atoms, we're going to use the natural radical that is the fluorine radical, kind of diffuse it to the surface, and we're going to hope to get SiF2, which is a very volatile gas, and use some of the ionized species or other particles made from that plasma to kind of wick away some of our silicon from the surface. That's kind of how that plasma etching is being used. So as you can tell from this, it is still using chemistry and reactions as a mechanism to kind of wick away some of the stuff from the surface. It does have some physical nature to it because we're transporting it, but the pressure within our chamber doesn't really allow high levels of kinetic energy as our mean free path is still pretty low. So moving on to reactive ion etching, this is still using chemistry for the most part. That's the type you see up there, just not just phi. You're still using chemistry to some point, but now it's being accelerated. So once we create our plasma, we do it here with a radio frequency, about 14 megahertz. At this frequency, the only thing that really reacts to it is the electrons, since they're so light. All our ions really aren't going to move with that frequency. Due to this, we get some pretty good mechanisms to try to accelerate ions towards our surface. You're going to see that our substrate, we kind of create a big layer of like negative charges there. So this allows us to accelerate pretty much any kind cation to that surface. So for reactive ion etching, the main use of for silicon is anything with a chlorine atom in it. They'll kind of sit around the surface like the same way fluoride does, but now those accelerating cations will come in, disrupt that SiCl chemisorption, and we'll get removal of them together as well as in a volatile gas, as said before. Here you can see just the anisotropic nature of it. You can see just how that aspect ratio of this trench being 32 to 3, so about 10 to 1. Yeah, so there's another way of doing dry etching. It's called ion milling. This is a 100% physical process. It requires high vacuum to get very large acceleration and high kinetic energy at our surface. Here we're basically just sputtering away our target substrate by just accelerating it. The plasma here actually is made apart from where the substrate is actually being seen. We just want those ions to be in the chamber, accelerate them, and hit our substrate as energetically as possible. So I think, yeah, that's all I got on photolithography and etching. Does anybody have any questions now before I pass it on to Lianen?
Sure, I have a question if you just happen to know it. For
Cool.
ion milling, do you know, I guess, what size features it can actually make with that? I'm assuming it's only on the micrometer scale at best.
Hmm. I myself don't know. I would assume, yeah, it probably wouldn't be much, I guess, larger than what reactive ion etching could do. But I do know your aspect ratio could get a lot bigger. So I know maybe instead of 32:3, I saw other images that showed like 1 micron compared to like 150 micron trench. So maybe something of that nature could happen with ion milling instead of what the reactive ion etching.
Okay, thank you.
Yeah. Anybody else? All right. Yanen, you're up.
Yeah, well, if there's no more questions, I will get into the vacuum systems. So vacuum systems, why are they important to the semiconductor industry? Well, most of the time, we have gas molecules in the environment that can interfere with the reactions or the processes. So it is useful to be able to remove gas molecules from the chamber, and some of the basic components include pumps, valves, chambers, and pipes. Um, and also the number of particles uh, in the chamber kind of dictates the mean free path. So the mean free path is basically the average distance that a particle will travel without seeing any other particles or colliding. And so when you have fewer particles in the chamber, it means that particles can travel a lot further without interruption. So you can see in this figure below that we have different levels of the vacuum. So we have like a rough vacuum, which can be at pressures from 1 atmosphere to about 1 millitorr, and then, or 10, wait, 1 millitorr, yeah. And then we have high vacuum, which goes even smaller in pressure, and then ultra high vacuum, which is even smaller. And the number of particles for each of these decreases as you increase the amount of vacuum. Do you want to move on? I don't have the PowerPoint control. Okay. And then, so we wonder, why are there so many different vacuums? Well, we also have many different applications. So the amount of vacuum that you need is determined by the application. So we're mainly operating with semiconductor processing and the thin film processing. So this could range from about 10 to the -9 torr to about 10 to the -1-ish. And so the chart is a little misleading because the pressures go down as you go to the right, but it just kind of means the vacuum, the amount of vacuum goes higher as we go to the right, and then weaker vacuum is like over on the left. And then, yeah, so we can do more things. Do you want to change the slide? We can do physical vapor deposition with the vacuum system. So the basic premise of physical vapor deposition is to vaporize a material, and this material accumulates on the surface of the substrate within a vacuum chamber. And then this vapor can be formed by heating up a metal, or it can be from physical bombardment of a target material. And this material usually is a solid for physical vapor deposition, although gases are used for chemical vapor deposition. And the variety of materials can be used with physical vapor deposition depending on the type of method that you are using. So metals, alloys, and organics can all be deposited. And then on this figure over on the right, this is actually our sputter slash thermal evaporator tool that we have in the teaching lab area. And so if you guys participate over the summer, you guys will get experience with how to operate this tool and perform metallization. So then one of the basic ways of doing PVD is thermal evaporation. So this one was the first one ever developed, first version of PVD. And this involves using resistive heating to heat up the source material, and it takes place in a vacuum chamber with pressure about less than a millitorr, and the material is heated until it vaporizes, and then it accumulates on the substrate, it condenses on the substrate. And historically, we were using this thermal evaporation for metal layers, but now sputtering is more common because there's better coverage. And temperature, the temperature really depends on the vapor pressure of the material that you are trying to deposit. So this could be a challenge when you are trying to deposit alloys, because alloys may have different vapor pressures, and if you have a large difference in the vapor pressure, then one may vaporize faster than the other, and so it could pose a challenge composition wise for alloys. Moving on to step coverage, it's pretty important to consider for PVD because all the PVD takes place in a vacuum chamber, and so the mean free path is longer because there's fewer particles around. And so for the case of thermal evaporation, it's very much a line of sight process where if you have anything blocking basically the path of the particle, then it does not get deposited. So things like trenches or different, tall features like fins on the surface may obstruct the view of the incoming particles. So there's different ways to account for this, but we can see in this figure here that the example part B shows the step coverage. It's not getting deposited on the left sidewall because of the angle that the particles are coming from. And so we can kind of fix this a little bit by using substrate rotation. So just rotating it about the vertical axis with respect to the substrate, and that can help vary the angles. And then also using multiple sources can also provide more angles that the particles can come from. And then using a planetary type substrate mount where the substrate is kind of located in a spherical type of mount where the substrate itself can rotate, as in the previous figure, part C, but also you can rotate the entire system around the vertical axis with respect to the target. And you can increase the conformity that way as well. So another method for physical vapor deposition is sputtering. Sputtering starts off by injecting a inert gas, such as argon, into the vacuum chamber, and then you apply a high voltage between the target and the substrate to generate a plasma. And then since it's composed of the positively charged argon ions, the positively charged argon ions will accelerate towards the target, knocking off particles from the target, and then these particles from the target get deposited onto the substrate. So there's some other variations of sputtering. We have magnetron sputtering, and then also RF sputtering. And magnetron sputtering is where magnets are placed behind the cathode, which increase the plasma density near the target. and this allows for much higher deposition rates. We can see in this figure that we have the magnets located behind the target materials, creating these magnetic fields that confine the electrons to be near the target material. And these electrons are what end up ionizing the argon gas and what forms the positive argon ions that can come and bombard the target. And so by confining them towards the target material, there's more of a chance that the electrons will create the argon ions, and then the argon, if there's more argon ions, then there's more particles that can come off of the target material. So a higher deposition rate. And then with sputtering or RF sputtering, we can deposit insulators such as oxides. So our original sputtering model just used a DC sputtering method where you never change the polarity of the voltage between the target and the substrate. So the issue with that for insulators has been that the charge builds up on the target material and then it just stays there and the material does not get deposited on the substrate. So by using RF sputtering and reversing the polarization between the target and the substrate, the charge buildup can be removed and accelerated towards the substrate. And then we all like some good comparisons. So we have our two simplest PVD techniques, sputtering and thermal evaporation. Sputtering tends to be more accommodating in terms of the materials that you can use, whereas thermal evaporation, you're restricted to metals, and it also struggles with alloys, whereas sputtering, you can do alloys, you can do organics, you can do a bunch. And then the step coverage is also better for sputtering, whereas with thermal evaporation, the step coverage is worse. This is kind of related to the vacuum needed. So the vacuum needed for sputtering could be low or high vacuum, whereas thermal evaporation requires a higher vacuum. And so if we translate that over to pressures, the thermal evaporation needs a even lower pressure than sputtering. And if we remember the mean free path concept where particles in a lower pressure environment would have longer mean free paths. So for sputtering with the higher pressure environment, they'll have shorter mean free paths. They'll bump into more particles along the way before reaching the surface. So they'll have naturally have more angles that they'll come from versus thermal evaporation where they just come straight from the target. And so the thermal evaporation is usually faster in terms of speed versus sputtering, which is slower. And then also the cost is more for sputtering, and usually the systems are like simpler and less expensive for thermal evaporation. Yeah, and that's all I have for PVD and vacuum systems. Does anybody have any questions?
Yeah, for the thermal evaporation deposition or sputtering, or no, deposition is what you use. What is the heat source that you use to actually evaporate these metals? Because we have a similar process in my lab, but we use a pulsed laser to do that. So I'm curious what you use. Or if you
Oh,
just
you
happen to
actually
know.
just use a conductive crucible and pass current through
Oh,
that.
okay.
Yeah. And so that heats it up. And that's why you're restricted to metals, because you have the
Mhm.
metal inside the crucible, everything's conductive, so everything heats up.
Yeah, that makes sense. If you
Uh,
use a pulsed laser, just so you know, in case you're curious about this in the future, you can use some really complex alloys with that, and
Yes.
that works.
yeah,
And
that's
I
what I,
heard pulse laser is very good with preserving the stoichiometry and everything.
yeah.
Mhm.
Are you doing stuff with like superconductors, Dylan, or?
No, I mean, we do have a superconductor in our lab, but what we work on right now is tuning the conductivity of materials by applying electric fields to them. So we have to use some pretty
Different
exotic alloys.
Yeah. Okay. Okay. Cool.
Mhm.
Yeah, so that's the end of the lecture series. We're gonna send out more information on like days of the week for the lab sessions over the summer. The main thing we're waiting on is communicating with the mentors. So once we get that in order, we'll be able to send an email out so that everyone knows when they're coming in. Yeah, but basically that's it. So you guys are free to go. Thank you for coming.
Yeah,
All right,
thank
thank you for
you.
having us.
Yes, of course.